Welcome to Mathematics 3. My name is Neil Koss. I'm going to start by giving some information about this course. At this university, through engineering students, we offer 4 mathematics courses. First 2 you've taken already. These are about a type of mathematics called calculus. In this course, we're going to move to a completely different type of mathematics. We're going to be talking about a type of mathematics called linear algebra. And then in mathematics 4, if you take that, that's again a different type of mathematics, but a mathematics which uses both calculus and linear algebra to solve differential equations. I'm expecting to give 12 classes to you, and they will be on Monday afternoon between 2 o'clock and 4 o'clock. There should be enough space in the term for 13 classes, but because something always comes up, we always lose a lesson. Usually we lose a lesson. I'm planning 12 lessons, and then we can make changes later if necessary. And the way I'm going to teach is I'm going to give you 2 lectures with a break in between them. And then after that, I'm available to answer your questions. The book for this course, we're not going to be using Thomas's calculus anymore. We have a new book. We're going to be using linear algebra and its applications by Lay, and MacDonald. It doesn't matter if you get the 5th edition or the 6th edition. I imagine most of you will be getting the 5th edition because the 6th edition is not widely available yet. This is a required purchase. You need to buy this book to be able to do the homework. This semester we're going to be talking about these topics: linear systems and their solutions, matrices, determinants, etc. And if we have time, we'll finish with singular value decomposition. If you look in the course material section of Echelon, you'll see there's a more detailed syllabus there. There's also a syllabus in a Word file which tells you which sections of your book you should be reading each week. We're going to be examining this course using both exams and homework. There will be homework, which uses Pearson's MyLab math system. I'm going to be setting 12 pieces of homework, so they will roughly line up with the lectures. For each lecture I give you, there will be 1 piece of homework on the same topics. The deadline for the homework will be 1 day before the final exam, whenever that is. I put in a temporary date of the 23rd of May, and then after we learn the final exam date, I'll change the deadline as appropriate. When you register for the homework, make sure you use the links inside Olearn. Olearn, because the Pearson course is integrated with Olearn, if you try to go to the MyLab website first, you can have errors when you try to register for it. So for the best plan is to log into Olearn first and then click the homework links. There'll be 2 midterm exams. These are going to be face-to-face. I'm guessing the first one will be in week 8, but that's not confirmed yet. And then at the end of term, there will be a final exam, which will also be a face-to-face exam. If this was a classroom course, then you would have 4 hours of lectures every week. And the expectation is that for every hour of lecture, you would study another 1 or 2 hours outside of class. So if this was a classroom class, you would be expected to study somewhere between 8 and 12 hours every week. For an online course, that's still true. You're still expected to study between 8 and 12 hours each week. But because we only have 2 hours of class time, that means you're going to be studying by yourself for an extra 2 hours. What could you be doing in this extra time? Well, there's the homework you should be doing on MyLab. Because the deadline is at the end of term, if you really want to, you can wait until May before you do all of the homework in one go. But I don't think that would be wise. Most people learn mathematics by doing a little bit every week. So I would encourage you to try to do one piece of homework each week instead of leaving them all to the end. I will make recordings of these lectures available in both Okan and also on YouTube. I will make all of my lecture slides available to you. The first 4 are ready already. I'm partway through writing the 5th one. You can find them in Okan. Read them before the lectures, read them after the lectures, up to you. Of course, you should be reading the textbook. As I say, if you find the Microsoft Word document in the course content section, that tells you which sections of the textbook you should be reading each week. You should be solving the exercises in the textbook, not just doing the homework on MyLab, but also try to solve as many exercises in the textbook as you can. And if necessary, use the discussion board in Okan. I'm checking this almost every day. If you have a question, then ask it there. If you see another student who's asked a question that you know the answer to, then answer them. And if you're available, you might like to read other books about linear algebra, either in English or in Turkish. If you look online, on YouTube, for example, there's many videos about linear algebra. Perhaps you might like to watch a lecture by another lecturer. And before I start, let me just point out the slide number is always at the bottom left. So you can see roughly how far we are through today's class. Now I'm ready to start today's lecture. Today I want to talk about 2 topics, systems of linear equations, and then we'll take a break, and then I want to talk about row reduction and echelon forms. A linear equation is an equation which looks like this. We have some variables, x1, x2, x3, etc. And we have some numbers, a1, a2, up to an, and b are numbers. They might be real numbers, they might be complex numbers. If we have an equation which looks like number variable plus number variable plus, and so on, plus number variable equals to number. If it looks like this, then it's a linear equation. If it doesn't look like this, then it's not a linear equation. Now, note, all of the variables are separated. There's one x1, there's one x2, there's one x3, and so on. We don't have them multiplied together. We don't have anything complicated like x1 squared. There's no sine x. There's nothing complicated. It's just number multiplied by a variable in each term. We say that again, just number multiplied by a variable plus number multiplied by a variable and so on, and then equal to a number. Nothing more complicated than that. In this course, n, how many variables we have, will usually be between 2 and 5, but when you start using this type of mathematics to do your engineering, n might be 50 or n might be 5,000 or perhaps bigger. These 2 equations are linear equations. Why? Because we can rearrange them so they look like the standard form, which I've written in the yellow box at the top. The first equation can be written as 3x1 minus 5x2 is equal to minus 2. So it's number variable plus number variable, the number is minus 5, is equal to a number. And the second equation, 2x1 plus x2 minus x3 is equal to 2 root 6. Again, this is number variable plus number variable plus number variable is equal to number. The first of these two equations is the equation of a straight line, and the latter is the equation of a plane. These two equations are not linear. They don't look like the standard form. It's not possible to rearrange them so they are the same as the standard form. The first one has variable multiplied by variable. We can't have anything like that in a linear equation. Nothing more complicated than number variable plus number variable plus number variable. The second equation has square root of x1. We're not allowed square roots either. Nothing other than just one variable on its own with no functions of it. If an equation is not linear, then we say it's non-linear. Now I have some questions to ask you. Look at equation 1 first of all. Is this a linear equation? Does it look like the equation in the yellow box? The answer is yes. Equation 1 is linear. It's 1x1, so just number x1, plus 1x2, number x2, plus 1x3, plus 1x4, plus 1x5, plus 1x6 is equal to 1. This looks like the form in the yellow box, so this is a linear equation. What about number 2? Is equation 2 a linear equation? Equation 2 is not linear because it has a squared term in it. It has x3 squared, and we're not allowed anything like this in a linear equation. What about equation 3? Again, most people are correct. Equation 3 is non-linear because it has a cos term in it. Equation 4 is linear. It's number variable plus number variable is equal to number variable. That's easy to rearrange so that it looks like the form in the yellow box. What about number 5? Again, most people got this correct. The variables are multiplied together, so this is a non-linear equation. This course is about linear equations. Typically, we would have more than one linear equation. Then we would have a linear system. That's a group of several linear equations. Here I have M equations. The first one is a number a11, x1, plus a number a12, x2, etc. And then the second one is a number a21, x1, plus some number a22, multiplied by the variable x2, plus etc. And the last one, and that's the mth equation, is a number am1, x1, plus some number am2, variable x2, plus dot, dot, dot. For example, 2x1 minus x2 plus 1.5x3 is equal to 8, and x1 minus 4x3 is equal to minus 7 is a linear system. A solution of a linear system is just a list of numbers which satisfies every equation in the linear system. So for example, 5, 6.5, 3 is a solution of this linear system. Why? Because if we replace x1 by 5 and we replace x2 by 6.5 and we replace x3 by 3 and then we calculate the left-hand side, we get equal to 8. And we do the same thing for the second equation. x1 minus 4x3, that's 5 minus 4 times 3 is minus 7. There's a typo here. The set of all possible solutions is called the solution set of the linear system. And another definition, two linear systems are called equivalent if they have the same solution set. For example, find the solution set of x1 minus 2x2 is equal to minus 1, minus x1 plus 3x2 is equal to 3. We've got two equations, and in each equation there are two variables. Each equation is the equation of a straight line. And I can show you the graphs of these in the x1, x2 plane. We can see from this picture that there's only one point which lies on both lines. Only the point 3, 2 is on the blue line and on the red line. So the solution set of this linear system is the set containing just the point 3, 2. What are the possibilities if we have two straight lines? Two straight lines might cross in or intersect in one point. They might be parallel or they might be exactly the same line. If these two lines intersect in one point, then we know that the linear system has exactly one solution. If these two lines are parallel, then there will be no solutions to the linear system. If the two lines are really exactly the same line, then we would have infinitely many solutions. What about if we had 3 planes, then it's also true. We might have 0 solutions. We might have exactly 1 solution if the 3 planes intersect in 1 point. Or we might have infinitely many points if the 3 planes intersect in a line, or if they intersect in the plane, if they're really just 3 different equations for exactly the same plane. And this is always true. A linear system has either 0 solutions, or exactly 1 solution, or infinitely many solutions. There's no other possibilities. We always have one of these. I'll prove the theorem to you in a later lecture, but for now, let's just carry on with our definitions. A linear system is called consistent if it has either 1 solution or infinitely many solutions. So if we're either in case number 2 or case number 3, then we say that our linear system is consistent. A linear system is called inconsistent if it does not have a solution. In other words, inconsistent means there are 0 solutions to the linear system. Consistent means there's at least 1 solution. The next idea is the idea of matrix notation. Have a look at this linear system. What is the important information here? Let me grey out some of this. The important information is the numbers. We don't need the xj's, we don't need the pluses, we don't need the equal signs. All we're really interested in here is the numbers. From the first equation, we have the numbers 1, -2, 1, and 0. Just write those numbers down. In the second equation, first of all, there's a gap with no variable. So I'm going to write 0 for that. And then the numbers go 2, -8, 8. And then along the bottom, -4, 5, 9, -9. Just pick out the important information and write it as an array of numbers. If we do this, we get an array of numbers which is called the augmented matrix for the linear system. Perhaps we're not interested in the orange numbers. Perhaps we only want the numbers I've written green here. Then we call this the coefficient matrix of the linear system. Okay, so how could we solve a linear system? Well, there's 3 things that we can do to help us solve it. We could multiply an equation by a number, or we could swap the positions of 2 equations, or we could add a multiple of 1 equation to another equation. We can do these and we don't change the solutions or the solution set of the linear system, but we could make it easier to find the solutions. For an augmented matrix, there's 3 things that we could do. We could multiply a row of the augmented matrix by a number, or we could swap the positions of 2 rows, or we could add a multiple of 1 row to another. These 3 things are called the elementary row operations, and these are things that we're going to be using many, many times in this course. So for example, solve this linear system. 1x1 minus 2x2 plus 1x3 is equal to 0. 2x2 minus 8x3 is equal to 8. Minus 4x1 plus 5x2 plus 9x3 is equal to minus 9. And at the same time that I solve this linear system, I'm going to solve another example at the same time. The second example I'm going to be solving at exactly the same time is use the elementary row operations to convert this augmented matrix into the form 1, 0, 0, and then some number which I don't know yet, 0, 1, 0, and then some number I don't know yet, and then along the bottom, 0, 0, 1, and then some number which I don't know yet. Before I do that, let me just make a remark. There's two things about the elementary row operations we should learn. We need to learn how to use these elementary row operations, and we need to learn why we choose a certain elementary row operation at each step. I'm going to teach the how first, and then in the second hour, after we've taken a break, I'll start talking about the why. So for now, just ignore or don't worry about why I'm choosing each row operation at each step. Just look at how we use them. Okay, here's the two examples. On the left, I'm going to solve this linear system. And on the right, I'm going to take this augmented matrix and I'm going to convert it into the form that I was asked to get to. First, look at the left. I want to do 4 times equation 1, and I want to add that to equation 3, and then that would be my new equation 3. So I'm going to take the first equation, I'm going to multiply it by 4, and then I'm going to add it to the third equation. So I'm going to do 4 multiplied by x1 minus 2x2 plus x3 is equal to 0. And I'm going to add that to minus 4x1 plus 5x2 plus 9x3 is equal to minus 9. And that will be an equation which I'm calling new equation 3. So let's add these together. 4x1 plus minus 4x1 gives 0x1. Minus 8x2 plus 5x2 gives minus 3x2. Plus 4x3 plus 4x3 plus 9x3 gives us 13x3. And 0 plus minus 9 gives minus 9. So that's my new equation 3. So now I've got to this point, which I'm circling in orange. Equation 1 and equation 2 stay exactly the same, but now I've got a new equation 3. Okay, that's step 1 for the linear system done. Now let's move to the augmenting matrix. Now look at the right-hand side of the slide. Now I want to do 4 times row 1 plus row 3, and that will give me a new row 3. The first row, written in red here, I'm going to call R1 for row 1. The orange numbers is row 2 or R2, and the blue numbers give me R3 or row 3. So multiply R1 by 4, I get 4 minus 8, 4, 0. And I want to add this onto the blue numbers, add this onto R3. So it's going to be plus, minus 4, 5, 9, minus 9. Four plus minus 4 is 0. Minus 8 plus 5 is minus 3. 4 plus 9 is 13, and 0 plus minus 9 is minus 9. This is my new row 3. So now I get a new augmented matrix. The red row stays the same, the orange row stays the same, but now I've got a new row 3. Okay, let's move on to step 2. this is where we got to last time. I've copied these from the bottom of the previous slide. For the linear systems, I want to multiply equation 2 by a half. For the augmented matrix, I want to multiply R2 by a half. First, the linear systems. Equation 1 and equation 3 stay exactly the same. Equation 2, I'm multiplying by a half, so I get x2 minus 4x3 is equal to 4. Now for the augmented matrix, I want to take row 2, that's 0, 2, minus 8, 8, and multiply by a half. I get a new row 2, 0, 1, minus 4, 4. Okay, let's move on to step 3. I'll copy the new linear system and the new augmented matrix again. This time I'm going to do the augmented matrix problem first. I'm going to take 3 times row 2 plus row 3, and I'm going to use this to be my new row 3. 3 times row 2 is 0, 3, minus 12, plus 12. And I'm going to add that on to 0 minus 3, 13, minus 9. 0 plus 0 is 0. 3 plus minus 3 is 0. Minus 12 plus 13 is 1. 12 plus minus 9 is 3. So I get my new augmented matrix. Now I'm making progress. Remember, we were asked to get zeros just here, and we were asked to get zeros just here. So I'm halfway there. I've turned 3 of the numbers into 0. I still have 3 to go. Now, look at the linear system on the left. I'm going to do 3 times equation 2, and I'm going to add that to equation 3, and that will give me a new equation 3. 3 times equation 2 is 3x2 minus 12x3 is equal to 12, and I'm going to add that on to minus 3x2 plus 13x3 is equal to minus 9. And what do I get? I get 0x2 plus 1x3 is equal to 3. So my new linear system looks like this. Now, step 4. Again, let's do the augmented matrix first. I'm going to do R2 plus 4 times R3, and that will become the new R2. So here we go. It's 0, 1, minus 4, 4, plus 4 times R3, so that's plus 0, 0, 4, 12. Add these together, we get 0, 1, 0, 16. So that's my new row 2. Look to the left now. I want to do equation 2 plus 4 times equation 3, and that will be the new equation 2. The new equation 2 is going to be x2 is equal to 16. Step 5. Again, augmented matrix first. I'm going to do row 1 minus row 3, and that will be the new row 1. The new row 1 is going to be 1 minus 2, 0, minus 3. And then we do pretty much exactly the same for the linear system. Equation 1 minus equation 3, and then we'll use that to be the new equation 1. The new equation 1 is x1 minus 2x2 is equal to minus 3. We're almost finished. One more step. For the augmented matrix, on the right, I'm going to do row 1 plus 2 times row 2 to give us a new row 1. Here's the calculation. The new row 1 is 1, 0, 0, 29. Now look to the left. I want to do equation 1 plus 2 times equation 2 to give me a new equation 1. My new equation 1 is x1 is equal to 29. Okay, so let's just summarize what we did. I was asked to solve this linear system, and I found that the solution is x1 is equal to 29, x2 is equal to 16, x3 is equal to 3. This linear system has one solution, exactly one solution. And in the second example, which I was doing at the same time, I was asked to use elementary row operations to convert the augmented matrix on the left into the form 1, 0, 0, some number, 0, 1, 0, some number, 0, 0, 1, some number. And the answer to this example is this one at the bottom. 1, 0, 0, 29, 0, 1, 0, 16, 0, 0, 1, 3. Two matrices, A and B, are called row equivalent if it's possible to change one into the other using elementary row operations. We have notation for this. We write A tilde B if A and B are row equivalent. Theorem. If the augmented matrices of two linear systems are row equivalent, then the two systems have the same solution set. So to solve a linear system, what we could do is we could write down its augmented matrix. We could use the row operations to change it into a simpler augmented matrix, and then we could go back to the linear system form and write that and find a solution. Whenever we do elementary row operations, we do not change the solution of our linear system. Let's talk about these elementary row operations again. Here they are. Number 1, we could multiply a row by a number. Number 2, I could swap two rows. Or number 3, I could add a multiple of one row to another row. Note that all three of these are invertible or reversible. What's the opposite of multiplying by a number C? The opposite is multiplying by 1 divided by C. What's the opposite of swapping two rows? Swap them back again. And what's the opposite of adding something? The opposite of adding something is just subtracting that something. Anytime we do one of these row operations, we can reverse it by doing the opposite. Let me just remind you, consistent means that a linear system has either one solution or infinitely many solutions. This example we just did has one solution, so this linear system is consistent. But what about this one? Is this linear system consistent? To answer this, we're going to take the augmented matrix for this linear system. We're going to do some elementary row operations on it, and we're going to see what we get. Okay, so we're starting with this one. We're starting with this orange augmented matrix. Step 1, I want to swap the positions of row 1 and row 2. So 0, 1, minus 4, 8 becomes the new row 2, and 2 minus 3, 2, 1 becomes the new row 1. And then I want to do row 3 minus 5 over 2 row 1 to become the new row 3. So first of all, I've got row 3, 5 minus 8, 7, 1. And then I'm doing plus minus 5 over 2 multiplied by row 1. 5 over 2 multiplied by 2 is 5. 5 over 2 multiplied by minus 5 over 2 multiplied by minus 3 is 15 over 2. Minus 5 over 2 multiplied by 2 is minus 5, and minus 5 over 2 multiplied by 1 is minus 5 over 2. And then add them together, we get our new row 3, 0 minus a half, 2 minus 3 over 2. Let's write this new one at the top. The next thing to do is the number I've written in a half. I have minus a half here, and I don't want this here. I want this to be 0. So the way to get rid of this is to do a half row 2 plus row 3 to become the new row 3. Here's the calculation. I'll leave this for you to check when you re-watch this lecture, or if you read the lecture slides. Check that I haven't made a mistake here, please. The new row 3 becomes 0, 0, 0, 5 over 2. Now I'm going to convert back to a linear system. So let's see what we have. First row is 2 minus 3, 2. That means 2x1 minus 3x2 plus 2x3, and then 1, so equal to 1. The second row of my augmented matrix is 0, 1, minus 4, 8. That means 0x1 plus 1x2 minus 4x3 is equal to 8. Or in other words, x2 minus 4x3 is equal to 8, and so on. And the bottom row says 0x1 plus 0x2 plus 0x3 is equal to 5 over 2. But wait a minute, equation 3 says 0 is equal to 5 over 2. And that's clearly nonsense. This means that it's not possible to find a solution to this linear system. If you get 0 is equal to a non-zero number, then you know that your linear system must be inconsistent. Let's do a similar example. For what values of h and k is the following system consistent? We need to take the augmented matrix, and we need to do, in this case, only one row operation. I'm going to do the row operation 3r1 plus r2 becomes the new r2. So the new r2 is 0, 0, 3h plus k. And in terms, or in notation of linear systems, the second equation is 0x1 plus 0x2 is equal to 3h plus k. So obviously, that's the same as saying 3h plus k is equal to 0. We need that to be true for the solution to have solutions. So the answer to this question is, this linear system is consistent only when 3h plus k is equal to 0. It doesn't matter if you use square brackets or rounded brackets when you write an augmented matrix. These two things are exactly the same. Square bracket 1, 2, 3, 4, 5, 6. Square bracket is exactly the same as rounded bracket 1, 2, 3, 4, 5, 6. Rounded bracket. So, for example, find an equation involving G, H, and K that makes this augmented matrix correspond to a consistent system. And this is notation. This is an example where it's using rounded brackets. And the only reason this is rounded brackets is because the place I copied this from used round brackets. This time we need to do two elementary row operations to make the third row 0, 0, 0, 2g plus h plus k. We can see from this that we need to have 2g plus h plus k is equal to 0 for a consistent system. Determine if the following system is consistent or inconsistent. If it's consistent, find all the solutions. Step 1, write down an augmented matrix for the system. That just means pick out the numbers. The numbers are 3, 5, minus 4, etc. So we write 3, 5, minus 4, etc. And then we're going to do row operations to simplify this augmented matrix. In other words, to get lots of zeros in here. And here's the whole calculation. I'm not going to talk through it this time. I'll leave this for you to check when you look at this again. The bottom row is now 0, 0, 0, 0. So that's 0x1 plus 0x2 plus 0x3 is equal to 0. That doesn't tell us anything. We can forget about that. Just forget about row 3. What are we left with? We're left with 3, 0, minus 4, minus 3. That means 3x1 minus 4x3 is equal to minus 3. And we're left with 0, 1, 0, 2. That means x2 is equal to 2. The first one we can rearrange to x1 is equal to minus 1 plus 403 x3. So therefore, every solution looks like this. Minus 1 plus 403 x3, comma 2, because x2 must be 2, comma x3. Or I could write this as x3 multiplied by a vector, 403, 0, 1, plus another vector, minus a half, 2, 0. Here, the x3 can be any real number. So that means there are infinitely many solutions to this linear system. Geometrically, this is a line. It's a line which passes through the point minus 1, 2, 0, parallel to the vector 4 over 3, 0, 1. You studied equations of lines in Mathematics 2. And then one more example before I take a break. Do the three planes, x1 plus 3x2 plus x3 is equal to 4, x2 minus x3 is equal to 1, x1 plus 4 over x2 is equal to minus 2, have a point in common. Explain. The question is really asking, is this linear system consistent? Is there one point x1, x2, x3 which satisfies all three equations, or is on all three planes simultaneously? So we take our augmented matrix and we do our row operations to simplify it. Look at the bottom line. The bottom row says 0, 0, 0, minus 7. What does that tell us? Row 3 of this augmented matrix says 0x1 plus 0x2 plus 0x3 is equal to minus 7, which of course is nonsense. That tells us that this linear system is inconsistent. It tells us that there's no solutions to the linear system. It tells us that there's no point in common for the three planes. And now it's time to take a break. And I think we'll take at least 10 minutes break. So let's take a break until 3:10. And now let's continue. For the rest of today's lecture, I want to talk about row reduction and echelon forms. First, what's this word echelon I'm saying? It's a word which comes from the military. An echelon formation is a formation in which the units are arranged diagonally. And this word is pronounced echelon because it comes from the French language. It's not Echelon, it's echelon. The first non-zero number in each row of an augmented matrix is called a leading entry or a pivot. So the number 2, that's the first non-zero number in the first row, is a leading entry or a pivot. In the second row, ignore the 0. The first number which is not a 0 is the 1. 1 is the leading entry or the pivot. Then here, this number 5 is a leading entry or a pivot because it's the first number from the left, which is not 0. And the bottom row goes 0, 0, 0, 0. Ignore those, ignore all the zeros. First number which is not 0 is the 6. That's a pivot or a leading entry. A matrix is in row echelon form, which I'm going to be abbreviating as REF a lot, if and only if the following 3 rules are satisfied. Rule number 1. All of the 0, 0, 0, 0 rows must be at the bottom. Looking at this matrix, we've got 2 rows of just zeros, these are at the bottom, and then the rows which have a number which is not 0 are at the top. Rule number 2. The leading entries or the pivots go down in this echelon formation, just like the planes in this photograph. They're going down diagonally. Every time we go down, we also go to the right. When we go from the 2 to the 1, we go down 1 and then right 1. And then we go down 1, right 2. And then again, if we're going from the 5 to 6, it's down 1, right 2. We're always going down and to the right. It's not straight down. It's every time we go down, we always have to move 1 or more columns to the right. And rule number 3, underneath a leading entry or a pivot, we have zeros. Underneath the 2, there's 5 zeros. Underneath the 1, there's 4 zeros. Underneath the green 5, we've got 3 zeros. And underneath the 6, we've got 2 zeros. If all 3 of these rules are satisfied, then we say that our matrix is in row echelon form. We also have another thing which is called reduced row echelon form. Not just row echelon form, but reduced row echelon form. And I'm going to be abbreviating that as RREF. And for RREF, we have to satisfy 5 rules. The first 3 are the same. All the 0, 0, 0 rows must be at the bottom. The leading entries or the pivots must have this echelon form, going diagonally down and to the right. And rule number 3, all of the entries below a pivot or a leading entry must be 0. We've got 2 more rules. Rule number 4, all of the pivots or all of the leading entries must be 1. For REF, we could have any number as the pivots, but for RREF, they must all be the number 1. And rule number 5, each leading 1, each pivot, each leading entry, which is a 1, is the only non-zero entry in its column. Look at the matrix at the bottom. Every time we've got a green 1, all of the numbers above it and below it must be 0. So for example, consider this matrix. Is this matrix in row echelon form? Is this matrix in reduced row echelon form? Let's bring up the rules and look at the rules. If it satisfies rules number 1, 2, and 3, then it's REF. But to be RREF, all 5 rules need to be satisfied. So let's go through these one by one. Are all of the 0, 0, 0 rows, if there are any, at the bottom? For this matrix, we don't have any 0, 0, 0 rows, so we could just forget about rule number 1. Rule number 1 is satisfied. Rule number 2, the leading entries or the pivots go diagonally down to the right. Where are the pivots? 2, 1, and 5/2. Yes, every time we go down, we also go to the right. So rule number 2 is satisfied. What about rule number 3? All the entries below a leading entry are 0. Let's see. Underneath the 2, I've got 0, 0. Underneath the 1, I've got 0. And underneath the 5/2, there's nothing. Yes, rule number 3 is satisfied. So this matrix is in REF. Is it also in RREF? Rule number 4, all of the leading entries are 1. No. I have a leading entry 2 and I have a leading entry 5/2. These are not 1. So rule number 4 is not satisfied. This matrix is in REF, but it's not in RREF. Let's look at another example. Consider this matrix. Is this matrix in REF? Is this matrix in RREF? Again, let's bring up the 5 rules. Rule number 1, all of the 0 rows are at the bottom. Yes. Rule number 2, the leading entries go diagonally downwards and to the right. This is a leading entry or a pivot, this is a leading entry or a pivot, and this is a leading entry or a pivot. They're going downwards and to the right. So we have this echelon formation. Rule number 3 is satisfied. So rule number 2 is satisfied, and we look at rule number 3. All of the entries below a pivot, below a leading entry, are equal to 0. So underneath this number 1, 0, 0, 0. Underneath this number 1, 0, 0. And underneath the third pivot, we get a 0. Rule number 3 is satisfied. So let's tick that. That tells us that this matrix is in REF. Let's next look at rule number 4. Are all the leading entries 1? Yes, rule number 4 is satisfied. And that just leaves rule number 5. Each leading 1 is the only non-zero entry in its column. Let's have a look. First column, 1 and then 3 zeros. Third column, we have our 1 and we also have 3 zeros. And sixth column, we have our leading 1 and we have 3 zeros. So yes, rule number 5 is satisfied. This matrix is in REF and in RREF. In this matrix, the pivot columns, that's the columns which contain a pivot, are the first column, the third column, and the sixth column. The pivot entries are the leading non-zero entries in the first, second, and third rows. We'll talk about that again later. And here's an example from, I think, your textbook or perhaps a different textbook. The first two matrices here are in row echelon form. Here, the black square could be any number which is not 0. The asterisks, the stars, could be any number, 0 or non-zero number. The third and fourth matrices here are in reduced row echelon form because the leading entries or the pivots are all number 1. Above and below each leading one, we have zeros. Two more definitions. A pivot position in some matrix A is a location in A that corresponds to a leading one in the reduced row echelon form of A. And a pivot column is a column in A which contains a pivot position. Theorem. Each row is row equivalent to one and only one reduced row echelon form matrix. That's not true for REF. There's many different possible REFs, but there's only one RREF form matrix. Before the break, I told you that when we were doing row operations, there's two things to learn, the how and the why. And I think I tried to explain the how then. Now it's time to start talking about the why. Why was I using a particular row operation at each step? We're going to be talking about a topic called Gaussian elimination. For example, I want to row reduce this matrix to row echelon form, and then I want to row reduce it further to get to reduced row echelon form. So how do we do this? How do we know which elementary row operation to use at each step? The answer is we need an algorithm. Step 1. We're going to find the first non-zero column. That's first from the left. Step 2, we don't want a 0 at the top of this column. So if necessary, we're going to swap the first row with another row. Step 3, we're going to create zeros under the pivot. Step 4, we're going to ignore the row and the column which contain the pivot, and then we're going to go back to step 1. And we'll repeat this process again and again and again until we get our matrix in REF. If we only want REF, then we can finish. But sometimes we would want reduced row echelon form, or RREF. And then we can move on to the next step of the algorithm. Step 5, we want to make every pivot a number 1 by multiplying rows by constants. And then finally, step 6, starting with the bottom rightmost pivot and then working upwards, we're going to create zeros above each pivot. If we've done that successfully, then our matrix should now be in RREF. If we want REF, if we want row echelon form, then we do steps 1 to 4, and this is called Gaussian elimination. If we want RREF, then we need to do all 6 steps, and that process is called Gauss-Jordan elimination. Another name which I'm going to be using is row reduction. Row reduction might refer to Gaussian elimination, or row reduction might refer to Gauss-Jordan elimination, depending on what we want at that time. So let's do this. Row reduce this matrix first to REF and then to RREF. Step 1 said first find the first non-zero column from the left. In this matrix, the first column is 0, -1, -2, 1. This column is not all zeros, so we're going to be using this column. Step 2. We don't want a 0 at the top of this column. So if necessary, swap the first row with another row. So I could swap row 1 with row 2, or I could swap row 1 with row 3, or I could swap row 1 with row 4. And I'm actually going to swap it with row 4 because the first number of row 4 is a number 1, +1, and +1 is an easy number to use. So I'm going to swap row 1 with row 4. Okay, let's move on to step 3. Here's our pivot, this green number 1. Create zeros under the pivot. Underneath the green 1, I want 0, 0, 0. So I need to do 2 row operations, and I'm going to do this in 2 separate steps. First, I'm going to do R1 plus R2 goes to the new row 2. Add row 1 and row 2 together. 1 plus -1 gives 0. 4 plus -2 gives 2. 5 plus -1 gives 4. -9 plus 3 gives -6. -7 plus 1 gives -6. That gives me 1, 0, and then next I want to change this -2 to 0. How can I do that? How can I combine a -2 and a 1 to get 0? I can do 2 times row 1 plus row 3 goes to row 3, because 2 plus -2 gives 0. Two times 4 is 8. 8 minus 3 is 5. Two times 5 plus 0 is 10. Two times -9 plus 3 is -15. And 2 times -7 plus -1 is also -15. Okay, now we've got our 0, 0, 0 here that we wanted. Time to move on to step 4. Step 4 says ignore the row and the column containing the pivot and then go back to step 1. So we're going to ignore the first row and we're going to ignore the first column. So just imagine that we actually have this matrix. Forget about the gray numbers for now. I'll leave them in gray because we'll need them later. But for now, just look at the black numbers. Just look at 2, 4, -6, -6, 5, 10, -15, -15, -3, -6, 4, 9. And then we're going to go back to step number 1. Step 1 said find the first column, which is not all zeros. I'll use this one, 2, 5, -3. I don't want a 0 at the top of this column. That's okay, I don't have 0, I have 2. Move on to step 3. I want zeros underneath the pivot. Underneath this green 2, I want zeros. So I'm going to do minus 5 over 2 R2 plus R3 goes to R3. And I'm going to do 3 over 2 R2 plus R4 goes to R4. And because I've chosen those correctly, I get my zeros here, which I wanted. Step 4 said ignore the row containing the pivot and ignore the column containing the pivot. So we're going to ignore row 2 and we're going to ignore column 2. Just look at the black numbers. Find the first non-zero column. Well, this column is all zeros. We're only looking at the black numbers. We have 0, 0. So we don't want this column. We move to the next one. This column is not all zeros. This is the column that we want. We want a number which is not 0 at the top of this column. I don't want a 0 just here. So I'm going to need to swap 2 rows. I'm going to swap row 3 with row 4. And then I have a matrix which is in REF. Now it's time to move to step 5. We've got to this point. Now we're going to reuse row 1, column 1, row 2, column 2, etc. We're using all the numbers again. We want to make every pivot a number 1 by multiplying rows by constants. These are the pivots. The green 1, the green 2, and the green -5 are the pivots. We want these to be number 1s. The columns which contain the pivots are called pivot columns. The first column, the second column, and the fourth column are the pivot columns. How can I make these pivots all 1? I could multiply row 2 by 1/2, and I could multiply row 3 by -1/5. Now, let me just give you a warning here. This is the first time I think I've done 2 row operations at the same time. Be careful if you do two row operations in the same step. Make sure that you don't change the same row twice in one step, or you're going to end up with the wrong answer. When you get to the end of the course, I imagine that you will be very comfortable doing this. You can do 2 row operations or more in one step without a problem. But when you're starting to do this, I recommend you stick to just doing 1 row operation at each step until you're more comfortable doing this. Step 6 says, starting from the bottom rightmost pivot, so that's this one, and then working upwards, create zeros above each pivot. So first, I'm going to make this -3 a 0, and then I'm going to make this -9 a 0. So just doing 1 step at a time, 1 row operation for each step. I'm going to do 3 times row 3 plus R2 goes to R2. So it's going to be 0, 1, 2, -3, -3, plus 0, 0, 0, 3, 0. Add those together, we get 0, 1, 2, 0, -3. And then I'm going to do 9 times R3 plus R1 goes to R1. That gives me my 0 here. And then finally, I want a 0 just here. So I'm going to do minus 4 R2 plus R1 goes to R1. So let's think about this. 1450 minus 7. Multiply R2 by minus 4, but it comes minus 4, minus 8, 0, and then plus 12. One plus 0 is 1. 4 plus minus 4 is 0. 5 plus minus 8 is minus 3. 0 plus 0 is 0. Minus 7 plus 12 gives 5. This matrix is now in reduced row echelon form. So just to recap, what we've done is we've taken the original matrix and we've used row operations to obtain a matrix which is in reduced row echelon form. These number ones, being written in green, are the pivots. Going back to the original matrix, the numbers which are in the same positions, that's 0, minus 2, and 3, are called pivot positions. The columns which contain either a pivot or a pivot position are called pivot columns. And that is the end of this week's lecture. Next week, I'm going to be talking about solutions of linear systems, and then I'm going to move on to more detail about matrices. I've been talking about augmented matrices this week, but I've deliberately been imprecise this week. Next week, I'll give more details about matrices, and then we'll start talking about the inverse of a matrix. This is the end of the lecture. As soon as I get to this orange slide, this is the end of the lecture. You can ask your questions now. Please feel free to stay logged in for however long you want. Please feel free to log out if you wish.